Hello everyone, welcome to Practical Mechanics. I'm Mohsen. Today we consider the position of a hole at RFS, MMC and LMC with position tolerance point 2. Let's start with an example. This is the case that we are going to consider and find out what's the difference when a position is given at RFS, MMC and LMC. Okay, let's construct a table with actual mating envelope, geometric tolerance, and see what we have. MMC size of the hole is 9.8. And then step by step, we approach to LMC. 10, 10.1, 10.2. That's LMC size of the hole. Geometric tolerance, because it says RFS says what? Regardless of feature of size, for all of them is the same. Let's find out conditions of this hole at MMC size and at LMC size. RFS means that rule number 1 does not apply. And for all sizes, you're allowed to have 0.2 error in position. Let's consider the position, for example, here. This is the true position of the axis of the hole. And we draw a circle. We draw a circle which is equal to 9.8. Ideal case. We consider ideal case here. Then we talk about its position tolerance. This is the hole. Ideal case that is not possible to produce. The hole without error, position error. Then designer gives manufacturer a zone which is equal to 0.2 for the error. It means that I know that you produce at the true position is impossible. I know that. I gave you a first actually space for this error. A space is given is equal to 0.2 means that if I drill here, the center at the here, then the hole, let's first be diameter is the same, fix it, and then at the center, draw a circle. I don't want to draw all of it, but the border of the hole is here. Assume that we drill at here, then the hole will be here. Assume we drill here, the border will be here, and the rest is outside of the ideal case, and assume we drill at here. Then if we change the center, from each side, it is displaced 0.1. This side is also 0.1. Top 0.1. Bottom down 0.1. And in any direction that you consider, the case of the hole, approaches one side 0.1 mm, and for the other side 0.1 inside. If we consider the largest cylinder inscribed with respect to these all circles that I draw, is a circle with from each side 0.1 inside, the real was 9.8. The true circle was 9.8, but we came 0.1 from the true circle. That's the true ideal circle. That is impossible to draw a hill exactly in the true position. Is 9.8, but we came 0.1 from side. For one hole, is it 0.1 right side. From other hole, other try, for other part, it is 0.1 left side. Other parts, 0.1 upward. Other part, 0.1 downward. Then, if I draw a circle that inscribe all of them, this circle shows the inner boundary of the hole. Then the inner boundary here happens at MMC minus geometric tolerance. Let's say show the size is inner boundary equals MMC minus GT. How much is it? 9.6. Hole can make at 9.8, but with error, any defects inside the hole or with the axis that displaces will be smaller for us if the goal is assembly. But RFS doesn't tell anything about assembly. What happened if we produce the hole at 10.2? Then assume that we draw another position tolerance here is again 0.2. That's the true position, and that's 0.2 for the circle. Assume first we assume that we make the case consider the ideal hole. Let's make it larger because it is 10.2. This is the ideal position of the hole. But we know that producing this one is not possible. We have a 0.2 error. What does it mean? It means again, the hole, instead of at this position, if we consider the center here, the hole will be here. I didn't draw the rest of the hole. Or if the center is here, the hole will be here. If the center is down, the hole will be here. If the center shifted up, the hole will be, edge of the hole will be there. Then, the smallest circle that you consider that encloses all this circle, or circumscribe all this circle, the smallest circle that circumscribe all this circle, encloses all these, is the outer boundary of the hole with this radius. correct it. Yeah. What does it show? It shows us that this is a boundary, which is called the outer boundary of the hole. If with any reason you consider that you produce at 10.2, but you have 0.2 error in position of the axis, or 0.2 error in the straightness of the axis, any geometric tolerance that can apply to a feature of size, then we have a border here that designer tell the manufacturer don't go outside of this border. This is if the ideal case was 10.2, then the circumscribed circle, the smallest circumscribed circle, should be this one, outer boundary, which is what? Which is equal to LMC size of the hole plus GT, which is equal to 10.2 plus 0.2, 10.4. That's a diameter. 10.2. Look at to here. What MMC tells us is that if in any reason it must be assembled, the size of the shaft maximum is 9.6, and the hole shouldn't be less than 9.6. Otherwise, assembly cannot happen. If there are adjacent parts, surrounding parts, actually this outer boundary introduces a region which we call the keep out region for the hole. Consider the shoulder of the road for a road, and that's keep out region that don't allow other people construct building or another thing or rest area or something like that. They must be far from the road. That's the keep out region of the road. For any holes that you make in any part, there is a keep out region. What is this region? It's the space between the minimum inner boundary and outer boundary. This belongs to the hole. Maybe a hole shifted. Maybe a hole is made at maximum size, LMC. Or is the minimum size, MMC. Okay? Then we must keep this region between inner boundary and outer boundary free. No adjacent parts are allowed in this region be mounted or assembled, because this belongs to the hole. Hole can be shifted, hole can be largest diameter, and also can be shifted. Then in this case, it approaches to this border. If you seems that, okay, the hole is here, I want to construct another part here, it will actually interfere with the border and keep out region of the hole. Okay, that's the inner boundary and outer boundary for position tolerance of a hole at RFS. Let's consider the other part with M modifier. See what will be changed if I put M modifier here. That's the whole size is true, geometric tolerance is true, but there is another column added here, virtual conditions, and there is 3 columns added here, boundless tolerance, total geometric tolerance, and resultant conditions. Let's calculate them. Okay. What does M modifier say? M modifier say, manufacturer, at MMC size, you are allowed to have point to error, not more, and then the bonus not given for MMC. And total geometric tolerance, the addition of these two is 0.2. But if you depart from MMC size, depends on the size after production. If you depart from MMC size, how much is the amount of departure? Here is 0.1. This is bonus. Here is 0.2. This is bonus. Here is 0.3. This is bonus, and here is 0.4. Then if you add them together, total tolerance error here, you can have 0.3, 0.4, 0.5, and 0.6. Okay. Let's see. What does M modifier say? M modifier says rule number 1 does not apply. M modifier says the important thing is the goal of this design is assembly. A shaft must go inside this hole. Then MMC size of the hole, which is the smallest size of the hole, is very important. Otherwise, it doesn't allow assembly. Assembly in this case. Then what we have? 9.8 with 0.2 displays is this was it. Conditions again. Then the hole can be 0.1, left and right shifted, or up and down, or in any other direction. The smallest inscribed circle that you consider that encloses the feature is less than 9.8. How much? 0.1 from both sides, which is 0.2. And again, the size is 9.6. This is what? Virtual conditions for the hole. This is called virtual conditions. And also the same is inner boundary. Okay, coincident with inner boundary. Then, in a set of virtual condition size, inner boundary, I can correct it to say virtual conditions at MMC size for a hole is MMC minus GT. Okay? It says that if you made it with these conditions, that after subtracting of the error, still there is a space for me 9.6, I can install the shaft. Can be assembled. Let's go for the LMC size. Then these virtual conditions is coincide with inner boundary of the part as well. Let's go for the outer. Okay, that's the important part in this modifier. We are worried about this size, and we make sure that we have 9.6 smallest size for the whole with actually corrected error is 9.6. Let's consider where it is at LMC. You produce it with, instead of point to error, we have a geometric zone 0.6, 0.3, 0.3 in all sides. Then the hole with the size 10.2 can be 0.3 shifted to the right side, can be 0.3 shifted to the left side, can be 0.3 shifted upward, can be 0.3 shifted downward, or in any other direction. We consider the smallest circle, circumscribe all these circles, encloses all these circles that I draw, based on a circle with the center here, 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 and at any other point. There are lots of circles. Any circuit that encloses all of them produces the resultant conditions and coincides with outer boundary. How much is it? LMC size plus geometric tolerance, which is the addition, total geometric tolerance, which is the addition of bonus and geometric tolerance, which we called it TGT, both sides. Here, it is not 0.2, it is 0.6. This is 10.8. Then here, you can write RC conditions belongs only to this size, 10.8. The same story here. The region between 9.6 and 10.8 is keep out region for the hole. Hole can be shifted, depends on the size, approaches to 10.8, approaches to 9.6, the size 9.6. It can be between them. It depends on the part, at which size it is produced. Then you must consider all possibilities. If you produce 1 million of this part, this whole, consider all of the cases. All this region may be actually is taken by the different holes. Okay? This is why we need inner boundary, we need outer boundary, and virtual conditions, which plays the role of inner boundary in this case. Let's consider when we have a position tolerance at L modifier. What does it mean? I change M to L. What does it mean? First, rule number 1 does not apply. Even at LMC, you can have 0.2 error. This is the meaning of L modifier. Bonus tolerance is also permitted. And the most important point here, when designers use L for the whole, they mean material sufficiency. What does mean material sufficiency? Look at to this design here. Material sufficiency when we use L means we are worried not about assembly, we are worried about the wall thickness. The question is this. If you make the hole with largest size close to LMC, is there enough is not the technical term here, is there adequate or sufficient material between the edge of the part and the surface, inner surface of the hole to protect the hole? Otherwise, the plate or the part close to edge, because of the hole, will crack. Fracture and crack can happen if the material is not sufficient to support the edge of the hole. Okay? How we can tell this message to manufacturer? By using L modifier. Okay, if I use L modifier, this bonus tolerance is permitted, but not like this. And total tolerance is permitted, but not this amount. RC is not this as well. And we calculate the rest. Okay. At LMC, you must stick to 0.2 error, not more. Why? Because you make the hole at largest size, and the error must be smallest. Otherwise, when the size is larger and error is larger at LMC, you approach to the edge of the plate or the part. And the part will be actually scrapped. Again, no bonus at this point. And total bonus is 0.2 again. And how much you departure from LMC 0.1? You can have bonus. Here 0.2, here 0.3, here 0.4. That's a departure from MMC. Total tolerance 0.6, 0.5, 0.4, 0.3, and minimum 0.2 for LMC. Okay, let's consider it. First, LMC. If you consider LMC, this should be 0.1 and 0.1 here, because the total geometric tolerance for position at LMC that you produce at 10.2 is 0.2. It says that at L modifier says that at LMC, consider the hole here. I must correct them. All of them is 0.1 down, 0.1 right side, 0.1 left side, 0.1 upside, 0.1 to any direction. Then you encloses all these circles with the smallest circles. Circumscribe the smallest circumscribed circle that encloses all is the outer boundary here. And this outer boundary is our goal. Actually, is the virtual conditions. How much is it? 10 LMC plus GT, 10.2 plus 0.2 error is 10.4. That's the virtual condition size. And coincide with what? Outer boundary. Okay? It means that manufacturer, if you make the hole at its maximum size, largest size, larger diameter, which is 10.2, and this 10.2, axis of this 10.2 can be 0.1 displaced to the right, can be 0.1 displaced to the left, and then you draw a circle with 10.2 plus 0.1 here, 0.1 other side. It cannot happen for a part, but if you produce many parts, sometimes they are shifted to left, sometimes to right, sometimes top, sometimes bottom, then you can draw many holes, and all of these holes encloses by circumscribed circle, which we call it the smallest circumscribed circle. That's the outer boundary of the hole. Then you approach it to the edge of the part in this case. Not more than 0.2 error is given. If you have a 10.2 and more than 0.2 error, for example, 0.3, 0.4, the thickness of the material will be thin and thinner, and there is no sufficient material to support the hole and the part in this case. And fracture happen, cracks happen. Okay, then let's consider the MMC size. At MMC size, position tolerance is 0.6, not 0.2 anymore. This is true position considered, and this is 0.6 error. It means what? 0.3 to the right, 0.3 to the left. That's 0.6 that is give you total geometric tolerance. If you draw them instead of 0.1, you get 0.3 inside, 0.3, 0.3, 0.3. We consider the inner border of the hole when you produce at MMC, smallest diameter of the hole, and you made a mistake, go 0.3 down or up or left or right, the hole comes down. One part holds 0.3, 0.2, 0.3, 0.3 comes down. For another part, it's 0.3 upward. For another point, 0.3 to the left. For another point, 0.3 to the right. If you inscribe a circle between all internal points, the largest circle that you can inscribe in this case is the inner border of the part. The largest inscribed circle. Here is the smallest circumscribed circle. Here is the largest inscribed circle. This is the inner boundary. What does it mean? It means that again here between inner boundary and RC conditions here, is 9.8. Let's complete the calculations. 9.8 is the ideal case, but not this one is not virtual conditions anymore. Is inner boundary, yes. What is the resultant conditions? MMC minus GT, which is equal to what? Is equal to 9.8 minus 0.6, 9.2. Then for RC here, we have 9.2, which is coincide with inner boundary. That's a difference. 9.2 is only for MMC size. If your size is different, RC resultant conditions, if the size is 9.9, then you have 0.5, which will here 9.9 minus 0.5 is 9.4, not 9.2, the resultant conditions. But we consider the minimum one. Why? We consider the minimum one because we wanted the inner boundary. The others are okay, as long as the inner boundary and virtual conditions solve our, let's clarify this 10, which is like 6. It's if I close to the edge of the part and make it 10.2, that's the worst case scenario. This is here, worst case scenario for designer, because the goal was material sufficiency. That's the difference between RFS, MMC, and LMC. Thank you for watching. See you in the next video.